All right, welcome everybody. Excited to be here. We are going over the Unit 7. We're starting today on Pythagorean theorem. Hopefully by now you know how the Pythagorean theorem works, or at least you've seen it before. We know the Pythagorean theorem says we have a squared plus b squared equals c squared. Now, what does that really mean? Because that's kind of a funky little trick. It's like, we just do it? I don't know. I'm not one for saying just believe it. That's how it works. We're good to go. So I want to pull up a couple of images that I think are super helpful. When we look at the triangle in this scenario here, we're using what's called a Pythagorean triple. That just means that we have a triangle that all the side lengths are whole integers. There's no decimals. When we look at a 3, 4, 5 triangle, we know that that's always going to be the case. It's always going to be that number. So if you ever have a triangle that has 3, 4, you know the hypotenuse is 5. Any arrangement of sides in there, we can determine the rest. Notice the way they've visualized this. We have a box. It's 3 by 3 or 9 units squared. We also have another box here, which is 4 by 4 or 16 units squared, and we have a 5 by 5 or 25 units squared. The green box plus the red box is supposed to equal the blue box, and numerically, they do. That's kind of a cool visual for this. Again, we have to have a right triangle. If it's a right triangle, we can follow through with this. That's one example. Another visual example I really like is this setup. If we take this side here, we know we have a plus b times a plus b. We can go into a mathematical proof, which we will hear in a second. But for now, let's just look at this a side. That is a squared. This white space or blank space, a negative space if you're an art goer, is a squared. And we have another one here, b squared. If we rearrange these triangles labeled Roman numerals 1, 2, 3, and 4 to around the perimeter of this same squared region as we had here, we have a c by c or c squared negative space. Visually, we can see that a squared plus b squared makes up all of the negative space, and c squared makes up, in this square to the right, all of the negative space. So a squared plus b squared visually equals c squared. Now I have one more proof. It's the algebra proof for this. It's a pretty straightforward proof, but we're going to start with that same image. That blue area here, there are 4 of those triangles, and all of those, if you were to look at the area of one of those triangles, is a times b divided by 2. Take that times 4, and that's 4 divided by 2 times a times b, which gives us 2ab. We're saying that is the area of the blue space. Now we also have c times c here. That is the area of the yellow space, c squared. So we have 2 times a times b plus c squared equals this larger box. Again, though, we're dealing with right triangles. That's all we really care about. So we're going to do a little bit of math down here and compare these. So there's that 4 times a times b over 2, or 2ab, plus a c squared equals the whole area. Good to go. If we use the polynomial distribution, so a times a times b times a, b times b, we end up getting c squared plus 2 times a times b. When we set that equal to our original calculated or determined setup here for the whole the whole box, the whole square, we can actually go and mathematically create, first of all, note that they're the exact same outcome. But second of all, note that we actually have 2 equations equal to each other, and when we subtract this missing piece here, we get 2ab. I will leave a link of this in Schoology. It should be in the supplementary section for Chapter 7, so you can go and check this out. But mathematically speaking, we can prove that we have 2 triangles, or sorry, 2 equations that equal the same thing and help us calculate mathematically the Pythagorean theorem. So now going back to our setup here, let's do some practice. As an example, we have here our hypotenuse is equal to the leg squared plus the leg squared. We don't give any numbers in there or anything else. This would be the equivalent to a squared plus b squared. We're going to plug the values that we found here and here. Again, we're using the side lengths, not the hypotenuse. So the side that's the longest or opposite this 90-degree angle is the hypotenuse. We are not using that as an a squared or b squared term. So I know we have this c squared or x squared equals this plus this. Make sure that when you add two values together, you are not adding one of these side lengths and the hypotenuse. That will give you an incorrect result. I've seen it done. Don't do it. We have numbers given of 36 and 64. We add those together. We get 100. Square root, again, this whole equation of a squared plus b squared equals the hypotenuse squared. We're saying the square of the length of the hypotenuse. That means it's not exactly the hypotenuse. It's more than that. We just have to square root that term to get down to the end. So we're going to go over a couple of examples here to get some practice, and then we're going to talk about the next part, which is just the converse of the Pythagorean theorem, which will be pretty intuitive now that we have this under our belt. All right, so now we have an example, actually a couple of examples here. We're going to start with this one on the left. We need to create the equation so that we can see something to work with. First, we need to identify the unknown side length is a hypotenuse or a leg, because we need to know if we're setting it up as c squared equals a squared plus b squared, where a and b are given, or if it's going to be c squared minus a equals b, because we're having a hypotenuse that's a given value and solving for the leg. And in this example, we have just that. We have a hypotenuse given, so we're going to go ahead and write it. I put the caret symbol in here as a to the power of. So just imagine, you'll see it in the calculator, it'll be to the power of 2. We're going to take that and we're going to, sorry about that, 5 to the power of 2 plus, I know what the is. We're going to change this box length a little bit to give us some area to work with. Awesome. 5 to the power of 2, notice we put the plus in there, wrong, right? We're saying that is equal to x to the power of 2 plus 3 to the power of 2. Not super useful because we need to get x by itself, but we can do that quite simply by subtracting 3 to the power of 2. 3 to the power of 2 from both sides. And now we have our setup. In the calculator, we'll go ahead and type that in. 5 to the power of 2 minus 3 to the power of 2. And that gives us 16. The square root of 16 is 4. We have a 3, 4, 5 triangle. Again, if you remember in our setup here, the example given on this problem, we have 3, 4, 5 triangle. Again, that's a Pythagorean triple. Whole list of those problems. We don't need to worry so much about those, but we have a whole list of those that we can work with. So now going into this one, our setup, notice again, we're looking for our C, our A, or our B, and which one is the one that's not given. Turns out it's the longest side, c squared. So we can go ahead and say c squared is x squared equals 6 to the power of 2 plus 4 to the power of 2. Notice again, I have the answers here given. We're trying to prove that those answers are in fact true. If we're right, then we've done it right. Here we're looking for 2 roots of 13, so let's check and make sure. We don't have to do any more arranging. We're all in the right place. So we would go ahead and calculate that out as 6 to the power of 2 plus 4 to the power of 2. And that gives us 52. Again, taking the square root of that, it's going to give us 2 roots of 13. Your calculator, depending on how it's set up, may give you a decimal. I don't personally care one way or the other. In a science class, they don't want you to do this. They want the decimal anyways. If you're looking for the exact answer because you're afraid of rounding errors, so if you're going to send somebody to the moon or any other type of long distance fit and every little bit counts, use these values here. But until then, this is going to be fine for the purposes of our class. You can look at how to simplify the radical. That's an algebra concept that we discussed, right? And if you need questions on that, I can certainly go through and show you that sometime. But that's the basic concept of the Pythagorean theorem. We have examples in real-world scenarios where we can calculate those out. I'm going to go ahead and forego doing those for now because you have those here as an example. We're going to get ready here for the converse of the Pythagorean theorem and a couple of other theorems, but pretty straightforward, and that will cover you through 7.1 and 7.2. So I'll be right back. All right, so we have here the converse of the Pythagorean theorem. That just simply means we're going the other direction. We said at first, if we have a right triangle, then if we can square both sides and add them together, it will equal the hypotenuse squared, and then we can solve. But it has to be a right triangle to then do those steps. So now we're saying if we do those steps and it works, and we have a squared plus b squared equals c squared, then we have a right triangle. So before we said assume a right triangle, then this is true. We're saying if this is true, we can then assume a right triangle, just go in the other direction. So if we go and look at these values here in this example, we have two. The first one given says 9 and 15. If we square those, they'll equal 306 when you add together. And 3 roots of 34 squared gives us 306 as well. We have a right triangle. Notice this example on the right. No good. 26 squared is 676, which is less than 680, which is the square root of the 22 and the 14. We do not have a right triangle. But we do have something of interest that we can look at here. We have two other theorems that say if your hypotenuse is less than the sum of a and b squared, so we square a, square b, and add them together, and c is less than it, you have an acute triangle. That should make sense. We're saying the hypotenuse is less than right. We have this angle here. I know this is not a perfect example, but if we say the hypotenuse is shorter, and it's still a triangle, it's going to bring those closer together. Now on the flip side, if we have the hypotenuse as a larger than the sum of a squared plus b squared, so c squared is larger than that, we have an obtuse angle. So those are the two special cases. Here's an example. You can pause it and look at it if you want to. We'll go ahead and move down. They have an example of an activity we would have done in class where we could take two right triangles and determine if this line is exactly perpendicular or not. It's kind of a neat little use for the converse of the Pythagorean theorem, saying, do we have a right triangle based on the numbers? Here are some concept summaries for the two theorems and the original converse. Understand again, these are theorems based off the chapter. Unless you're going to use this chapter for everything geometry related, probably not. This is better just to understand that these are the obtuse and acute theorems related to the Pythagorean theorem. I'm sure you could pull that up anywhere else. There are some exercise examples, answers, things like that if you want to look at those for practice. But other than that, that sums up this lesson and the introduction to Chapter 7 dealing with right triangles, similar triangles, things like that. Hopefully this helps going forward. If you have questions, please let me know. I'd be more than happy to work through more examples to get you a better idea.